Welcome to our annual Lifetime Physics Awards. This year's recipient is the late James Clerk Maxwell. As we celebrate the achievements of Mr. Maxwell, I would like to recognize the life and accomplishments of the man who many consider the father of modern physics. James Clerk Maxwell was born on June 13, 1831 in Edinburgh, Scotland, to Father John Clerk Maxwell of Middleby, an advocate, and Mother Frances Kay. Growing up, Maxwell was described to be very curious. By the age of 3, he was already asking questions on everything about anything. In a letter written by his mother to his aunt, she wrote, "Maxwell has great work with doors, locks, keys, etc., and show me how a deuce is never out of his mouth." Maxwell's mother recognized his potential and took responsibility for his early education. However, when she passed when he was only 8 years old, Maxwell's father decided to send him to Edinburgh Academy, where his zeal for learning would only become more insatiable. Though underestimated by his peers most of his childhood, his intelligence shone through when he began to win many of the highest prizes in the academy for mathematics and English. By the age of 14, Maxwell had already written his first scientific paper on ovals, called oval curves. At age 16, Maxwell began attending the University of Edinburgh, where he studied natural, moral, and mental philosophy. At age 18, already an accomplished mathematician, Maxwell left for the University of Cambridge to further study mathematics and obtain a fellowship. In 1856, Maxwell was appointed chair of natural philosophy at the Marischal College of Aberdeen. This is where he would meet his wife, Catherine Mary Dewar, and write a paper on the rings of Saturn. In 1857, Maxwell concluded that the rings of Saturn were composed of particles called brickbats, and the stability of them were satisfied by the mutual attractions and motions of the planet and the rings. This would be his first of many major contributions to the scientific world. From 1860 to 1866, Maxwell was a professor of natural philosophy at King's College in London. This is where he would perform his most important experimental work to physics, his formulation of the electromagnetic theory. According to Faraday's conception of electromagnetic induction earlier in 1831, an electric charge or magnetic pole was the origin of a line of force which filled in all directions of surrounding space and where electric and magnetic effects were produced. Force between positive and negative electric charges or between north and south magnetic poles were in a state of tension, attracting opposing forces. Maxwell linked Faraday's work into a set of equations which are famously known today as Maxwell's equations. Maxwell quantified that any changes in the electric and magnetic fields surrounding an electric circuit would cause changes along the lines of force which permeated the surrounding space. Maxwell's equations were based on 4 principal ideas. 1. Electric charge created electric fields. 2. Electric fields begin and end in charges, whereas magnetic fields did not begin or end, but were in continuous loops. 3. Changing electric fields produced magnetic fields. And lastly, 4. Changing magnetic fields would produce electric fields. Upon mathematical analysis, Maxwell found that the speed of this proposed electromagnetic wave would be approximately 3 times 10 to the power of 8 meters per second, the same as the speed of light in a vacuum. Thus, he would conclude, the velocity of an electromagnetic wave is so nearly that of light that it seems that we have a strong reason to conclude that light itself is an electromagnetic disturbance in the form of waves propagated through the electromagnetic laws. During his time at King's College, Maxwell also immersed himself in other fields of study, such as color and kinetic theory, confirming Newton's theory that all colors could be derived from the same 3 primary colors, red, green, and blue, as well as developing other formulas named Maxwell distribution and Maxwell's demons, generalizing all previous laws of thermodynamics. During his final years before succumbing to cancer in 1879, he worked as the first professor of experimental physics at the University of Cambridge and directed the newly created Cavendish Laboratory. This lab is where much of modern physics would continue to develop. Maxwell's formulation of the theory of electromagnetism became the stepping stone into modern physics. In 1887, German physicist Heinrich Hertz would produce these waves and furthermore find proof for the wave phenomena of reflection, refraction, interference, and polarization. In 1909, Nobel Peace Prize winner Giuliano Marconi created the first transatlantic radio communication using Maxwell's prediction of electromagnetic waves. Maxwell's contributions even reached Albert Einstein's work on his theory of special relativity. Where Einstein's theory of space and time upset almost all of classical physics, Maxwell's predictions remained untouched. Einstein would later attribute his revelations to Maxwell, saying, "There would be no modern physics without Maxwell's electromagnetic equations. I owe more to Maxwell than to anyone." Over the decades, the spectrum of electromagnetic waves has grown significantly. Maxwell's work has helped us understand phenomena from small wavelength X-rays used in medicine to longer wavelengths that allow us to use radio signals and watch the TV. All these modern conveniences continue to be made possible through the foundational work of James Clerk Maxwell, a pioneer in electromagnetism who made fundamental contributions to physics, mathematics, astronomy, and engineering. As Maxwell once said, it is when we take some interest in great discoverers and their lives that it becomes endurable, and only when we begin to trace the development of ideas that it becomes fascinating. Now, without further ado, it is with great honor and privilege that I present the Lifetime Physics Award posthumously to the James Clerk Maxwell.